Hey Matrix, welcome to the next video in the physics playlist. Today we're going over question 8 of the November 2020 past paper. If you don't have the paper, there's a link in the description down below where you can download the paper as well as the memo, and then we can continue with the video. Let's get started with question 8. Okay, so question 8 is dealing with circuits. Okay, so they say here that a battery with an internal resistance of 0.5 ohms and an unknown EMF is connected to 3 resistors. Okay, a high resistance voltmeter and an ammeter with negligible resistance as shown in the figure down below. Okay, so we've got our switch over here, we've got these two resistors in parallel, and then we've got another resistor in series over here, and then they've indicated our battery over here. Okay, the voltmeter and an ammeter. So 8.1 says define the term EMF of a battery. Okay, so you can go and check your definition list for the exact definition for EMF. Okay, I'm going to be starting with 8.2. Okay, so it then says the reading on the voltmeter decreases by 1.5 volts when the switch S is closed. Okay, so when S is closed, there's a potential change in the circuit of 1.5 volts. Now it says give a reason why the voltmeter reading decreases. Okay, so note that when the switch is open, okay, so open, no current flows. Okay, so there can't be a change in potential due to there being no movement. Okay, so the minute that the switch is closed, okay, we create the flow of current because now there's a potential difference. Okay, and due to the potential difference, there is internal resistance that takes place. So now because of internal resistance, so there's an increase in internal resistance, and remember the resistors in the series will use energy as well, and they convert it to heat. So due to the internal resistance increasing, there's an increase in heat in the circuit and therefore a decrease in voltage. Okay, now looking at 8.3, it says calculate the following when S is closed. Okay, so now S is closed, so we have current flowing over here. So now it says the reading on the ammeter. Okay, now note that the ammeter sits here after the two resistors. Okay, so note that the total current flowing in here, okay, will be the total current of the circuit. Therefore, the total current flowing out of here will be the total current of the circuit as well. Okay, now the ammeter is placed over here, but I could have placed the ammeter over here as well. It would have given me the exact same reading because it's taking into account the total current over here, and it's taking into account the total current over there. Okay, so think about placing the ammeter over there. What's the only thing that's giving us resistance? Well, it's the internal resistance over here. Okay, where are we getting our voltage from? Well, we know that from here it says a decrease of 1.5 volts. The change in potential in the circuit is 1.5 volts. So we have internal resistance, we have voltage, therefore we can calculate our current. Okay, so we know that R equals V over I. Okay, in this case we're going to have we're going to rearrange in order to get our current, so that's going to then imply we have current equals to voltage over resistance. Okay, so my current is then going to be my voltage 1.5 volts. Okay, because it's a change in potential all over the resistance, which is the internal resistance, which then gives us 3 amps. Okay, and that will be the total current for the circuit. Okay, now looking at 8.3.2, it says the total external resistance of the circuit. Okay, so this normally becomes a little bit tricky when we're trying to figure out what's in parallel and what's in series, but the best way is to draw your circuit out in one straight line. So what do I mean by this? Well, let me show you. So I'm going to start at S. Okay, so I am starting over here and I'm going to work around. I'm just going to flatten the circuit. So S then comes out, we then have a split for the two resistors. Okay, they then join again. Okay, now that they've joined, we have the ammeter A over there. We then come around, we come into contact with the R1. Okay, you could draw a block or the squiggly line, doesn't matter. Then we have our battery. Okay, we have the internal resistance of little r, and then we come back to our switch. Okay, so S and S. Okay, so now we can see everything in a straight line, and we can determine what's in parallel and what's in series. So note that R2 and R3 is then in parallel, and this entire branch is in series with R1. Okay, so now that we want to calculate the external resistance, we're going to have to convert these two into a combined resistor and then add it to this one. So we can say R23 is going to equal to 1 over R2, okay, plus 1 over R3, okay, or it can be written as R2, R3 all over R2 plus R3. Okay. Okay, now that we have that, we can plug in our values over here. So we know that for R2 it's 25, R3 is 15. So substituting that in there, it's going to be 25 times 15, all divided by 25 plus 15. And that is then going to give us a total resistance of 9.375 ohms. Okay, but now remember they wanted the total resistance. So now we've got to add this to this branch over here. So we can say R123, which is my total, is then going to be R1 plus R23, which is then going to give me 4 plus 9.375, which is then going to give me a total of 13.38, okay, if you round up, ohms. Okay, now looking at 8.3.3, it says the EMF of the battery. Okay, so now we know, if you look at your formula sheet, we know that epsilon, which represents EMF, okay, is equal to the total current of the circuit, okay, multiplied by the total resistance of the circuit plus the internal resistance of the circuit. Okay, so you can see it looks very similar to our V equals R times I. Okay, in this case we're just taking into account our internal resistance. Okay, so this is then going to be 3 amps. Okay, we've just calculated our total resistance, which was 13.38 plus 0.5, because that's our internal resistance over there. Okay, and that then gives us a total of 41.64 volts. Okay, and that's our then EMF of the battery. Okay, now let's have a look at 8.4. 8.4 says a learner makes the following statement: the current through R3 is larger than the current through R2. Okay, so R3 and R2. So let's check if this statement is true, and let's explain why it's true. Okay, so 8.4. Okay, so we know that resistance equals to voltage over current. Now we can see here that when we're dealing with current, it always takes the path of least resistance. So R3 is less than R2, so we can see that if we decrease our resistance, our current needs to increase. Okay, that's just because of the mathematical relationship saying that R is inversely proportional to the current. So if R decreases, I must increase. So we can say yes, his statement is true. Okay, why? Because the R3 is less than R2, therefore current is greater in R3. Okay, why? Because current takes the path of least resistance. Okay, now let's look at 8.5. 8.5 says the 4 ohm resistor is now removed from the circuit. How will this affect the EMF of the battery? Choose increasing, decreasing, or remain the same. Okay, now 8.5. Okay, so notice the formula for EMF says it's my current times the total resistance. Now, even though this resistance will decrease, okay, can you see here that EMF, if you look at the definition, okay, EMF refers to the amount of charge passing through the battery at any given point in time. Okay, so units per charge passing through the battery. So can you see that because I've removed this resistor over here, I haven't changed the total current of the circuit. Okay, so just by removing this resistor has no effect on the current of the circuit. Okay, why? Because the current's determined by the EMF or the internal resistance and the voltage drop over the battery. Therefore, removing this resistor does nothing to the EMF and it remains the same. Okay, and that's how we go about doing this question. Okay, if you found today's video helpful, then please leave a thumbs up on the video. It does help a lot. If you have any questions regarding question 8 of the physics paper, then please leave them in the comment section down below. I'll get back to them as soon as I can. Please go check out the channel as well. There's maths and chemistry past paper videos on there as well. While you're there, please consider subscribing to the channel. And remember, it's never too late to have an OIC moment.